Hi friends, in this video we are going to discuss about Euler Theorem. So before that I want to discuss about the homogeneous function of degree n. So a definition of the homogeneous function says a function f of x comma y is said to be a homogeneous function of degree n if degree of each term is n. So for example, let's say this is my function f of x comma y. Here in general function here I am written in terms of two variable x and y. A0 x to the power n plus a1 x to the power n minus 1 plus into y plus a2 x to the power n minus 2 into y square plus dash up to a to the an into y to the power n. So here this is my function in two variable x and y. The definition says a function is said to be homogeneous function of degree n if degree of each term is 1. So just focus on this is my function in two variable x and y. This is my first term, this is my second term, and this is my third term, and so on. This is my nth term. So degree of each term. So here degree of each term, that is degree of first term x to the power n, that is n. Degree of my second term x to the power n minus 1 plus y to the power n. So degree of my second term is also n. So here my degree of my first term is n, degree of my second term is n. In the same way, x to the power n minus 2 into here this degree of y is 2 and this is degree of x is n minus 2. So n minus 2 plus 2, that is n. So in the same way, this is my degree of nth term is n. So here how this is n? This is n. So this is n minus 1 plus 1. So this is 1. This is n minus 2 plus 2. This is n. In the same way, this is n. So here degree of first term is n. So n minus 1 plus 1 again n minus 2 plus 2. So degree of my third term is also n. So here this is my homogeneous function of degree n because degree of each term is n. Degree of first term is n, degree of second term is n, degree of third term is 1 n, and degree of nth term is again n. So another definition. A function f of x comma y is a homogeneous function of degree n, then it can be just replace x by kx, let's say, and y by ky, then f of kx comma ky equal to k to the power n f of x comma y, or and it can be so in terms of three variable. So here f of kx comma ky comma kz equal to k to the power n times f of x comma y comma z. Then you can say your function is a homogeneous function of degree. So this is n. Now, and it can be expressed as x to the power n into f of y by x or y to the power n into f of x by y. So here this is the definition of the homogeneous function of degree n. Now I will discuss. So I will discuss this example and I will show whether I will check whether the given function is homogeneous function of degree n or whatever the degree is 2, 3, 4 or not. So here I will check whether these given functions are homogeneous or not with respect to this condition. Now so according to definition, so definition of the homogeneous function says, so here let's say f of x comma y is a homogeneous, let's say f of x comma y is a function of two variable x and y is said to be a homogeneous function of degree, let's say degree n, then it can be written as f of, let's say replace x by kx comma ky, replace y by ky, which is equal to k to the power n into f of x comma y, or in other way, so degree of each term is 1. So here I will show with the help of this. Now my first example, so here first example is about, so here f of x comma y equal to x square plus x y, this is plus y square. Now just first observe one thing, this is my first term, so this is my first term, this is my second term, and this is my third term, and degree of my first term is 2. So here how to find the degree of my first term? So here degree of first term, here degree of first term equal to here x to the power of x. So power of x plus power of y. So here power of x plus power of y, which is equal to, now tell me, here I will write power of x is 2 and power of here y to the power 0 is 1. Here I will write y to the power 0 and power of y is, let's say, 0, which is equal to 2. So here degree of my first term is 2. So here degree of my first term is 2. Now in the same way find the degree of second term. So here degree of second term equal to, so again power of x plus power of y. This is x into y. Power of x is 1 plus power of y is 1, which is equal to 2. So here degree of my second term is also 2. Now come to the third term. So degree of third term. So degree of third term, which is equal to power of x plus power of y. Here x is not there, means x to the power 0 into y to the power 2. So here 0 plus 2, which is equal to 2. So here degree of third term is again 2. Therefore degree of each term is 2. That's why this is the homogeneous function of degree 2. Or by the definition of, so here replace x by tx and y by, let's say, ty. Here you can replace kx, replace x by kx or y by ky. Here I am taking t. Now here in this function f of tx comma ty, according to this function, how this function is defined? Tx square plus xy, that is tx ty plus ty, this is whole square, which is equal to t square, this is x square, this is equal to t into t square, this is x into y, plus t square, this is y square, which is equal to t square times, this is x square, plus this is xy, plus y square, this is equal to t to the power 2 times f of x comma y. So here t to the power n times f of x comma y. So therefore this is the homogeneous function of degree 2. So like this is degree of each term is 2. So this is the homogeneous function of degree 2. So here in this way also this is the homogeneous function of degree 2. So therefore my first function is a homogeneous. So here is a homogeneous function. So here my first function is, here I will write with the help of red pen. So here this is my homogeneous function. Here homogeneous function of degree 2. Now I want to write here I want to check my second function. Now here I will check in this way only. Now second function says, so second function is defined by, so here second function f of x comma y equal to x square plus y square. So this is my function which is defined by f of x comma y equal to x square plus y square. Now just check. So this is my first term and this is my second term. So here degree of my first term is 2. So here and degree of my second term is 2. So this is the homogeneous function of degree 2. Now I want to check with the help of this definition. Replace x by tx and y by ty. So I want to show. So here replace here x by, let's say, tx and y by ty. I want to show f of tx comma ty equal to t to the power 2 times f of x comma y. So tx comma ty, here this is tx whole square plus ty whole square, which is equal to t square, this is x square, plus t square y square, which is equal to t square times, this is x square plus y square, which is equal to t square times f of x comma y. So here this is a homogeneous function of degree 2. So here second function is also the homogeneous. So here this my second function is also homogeneous function of degree 2. So here second function is also a homogeneous function of degree 2. Now I want to check my third function. So here third function is defined by, so here just observe my third function. So here I will write my third function over here. Let's say f of x comma y equal to, so here x square plus y. Now here this is my first term. So here this is my first term and this is my second term. So you can observe the degree of first term is y to the power 0 into x to the power 2. So here degree of my first term is 2, but degree of my second term is 1. x to the power 0 into y to the power n, y to the power 1. So here degree of my second term is 1. Here degree of my first term is not same as degree of my second term. So anyhow this function is non-homogeneous. But I want to check this function. Here I want to show with the help of this definition. Replace x by tx and y by ty. So here this is my non-homogeneous function. But here I will show. Here just replace x by tx and y by ty. Here f of tx comma ty can be written as, so here first term square plus this is here t times y. So this is equal to t square x square plus t times y. So this is equal to, here I will take only t common. So t times, here this is t x square plus this is y. This is not same as t to the power, here either 1 times f of x comma y or t. This is not same as t to the power n times f of x comma y. Here n is the degree of my function. But here this is not same as either 1 or 2. So here this is not a homogeneous function. So here my second example is, this is my non-homogeneous function. Non-homogeneous. So second example is my non-homogeneous function. Now I want to check my third example, fourth example. So fourth example is defined by, let's say this is in 3 variable. So here let's say f of x comma y, f of x comma y comma z. If here this is function is defined as f of x comma y comma z equal to, let's say this is defined as xy plus yz plus this is xz. Now this is my first term, this is my second term, and this is my third term. Now observe one thing. In my first term x and y quantity, x and y variables are there. In my second term y and z, and in my third term x and z variable. Now degree of my first term, power of x plus power of y, 1 plus 1. This is 2. Degree of my second term, power of y, power of z. This is 2. Degree of my third term, power of x, power of z. This is again 2. So here degree of my each term is 2. So this is the homogeneous function of degree 2. But here I want to check this with the help of this definition. So here replace x by tx, y by ty, and let's say z by t times z. So here f of tx, ty, tz, which is equal to, so here product of this first two terms x and y. So here this is tx and ty. So here tx ty plus product of yz. So here product of these two. So here ty tz plus product of first and third. So x and z. This is tx, this is tz. So here which is equal to, let's say here I will write t square times xy plus t square times yz plus t square times this is xz. Here I will take t square common, t square times this is xy plus yz plus xz, which is equal to t square times f of x comma y comma z. So therefore this is the homogeneous function of degree 2. So here my third example is also, this is my homogeneous function of degree 2. So here third example is fourth example is also homogeneous function of degree 2. Now I want to here fifth example. Here I want to check my fifth example. Here let's say fifth example says, let's say here I will write my function f of x comma y, which is equal to 3x by y plus log of y by x. Now here this is my function is defined as f of x comma y equal to 3 times x by y plus log of y by x. So here if you want to write, I want to express this logarithmic function in terms of x and y as a polynomial. But here instead of that, first I want to go with the help of that definition. Replace x by tx and y by ty, and I will check. So instead of that, degree of first term, degree of second term, and degree of third term. So here I will replace x by here tx and y by this is ty. So here now f of tx comma ty equal to, so here this is 3 times, replace x by tx, y by ty plus log of, this is y, that y is ty, this is tx. So here tt gets cancelled, this is simply 3 times x by y plus log of tx, tt gets cancelled, this is simply again y by x. So here, now tell me, this is the homogeneous function or not? So here I will write this same as k to the power 0 times 3x by y. K to the power 0, let's say t to the power here 0 times. So t to the power 0 is nothing but 1. So here 1 into anything is no issue. Plus t to the power 0 times log of, this is y by x, which is equal to t to the power 0 times. So here I will take common t to the power 0, 3x by y plus log of, this is y by x, which is equal to t to the power 0 times f of x comma y. So here this is the homogeneous function of degree 0. So here my second function is also, my fifth function is also, this is my homogeneous function of degree 0. So this is my 0, not O. So now I want to check example number 6, whether this is the homogeneous function or not. Here, now here example 6 is defined by f of x comma y equal to log of y plus 2 times log of x. Now I want to check here, I don't want to express this logarithmic function y in terms of polynomial of y and polynomial of x. So here now I don't want to express, but here I will check whether this function is the homogeneous function of degree something or not. With the help of that definition, replace x by tx or y by ty. And so here I want to replace x by, this is tx, and y by, this is ty. So here f of x comma y equal to, f of x comma y equal to, so here tell me log of, this is k times y, t times y, here this is t times y plus 2 times log of, this is t times x. Now here log of a b equal to, here the property of logarithmic, log of a into b equal to log of a plus log of, here log of b. So here I want to use this property. Now tell me log of tx, this is same as log of here t plus log of y plus, this is 2 times here log of here t plus log of, this is x, which is equal to here log of t plus log of y plus 2 times log of t plus 2 times log of, this is x. Now which is equal to here 2 times log of t, 1 times log of t, 3 times log of t plus, this is log of y plus 2 times log of x. Now so here this is not 1 2 so 3 times log t plus log y plus 2 times log x. So here this is, we can't write this is same as here t to the power some n times f of x comma y. So here this extra term is there, so we can't remove this extra term. So we can't remove this extra term, and it is not possible to write this function with in terms of this. So here this is not 1. If this is 1, I will write t to the power 0 times something. But here this is not 1. Never, this term is never becomes 1. So that's why here I am unable to write. So here I am unable to write this function in terms of t to the power n times f of x comma y. So here this is the not homogeneous function. So here this is my this is not a homogeneous function. So here, so forget about definition. So about degree. So here this is my non-homogeneous function. Now we can't write this extra term came 3 times log t. That's why this is not a. So we can't write this function in terms of this form. So now I want to check my example number 7. Now here example number 7 is defined as f of x comma y, which is equal to, so here x to the power 1 by 3, y to the power 1 by 4 into tan inverse, this is y by x. So here x to the power 1 by 3, y to the power 1 by 4, tan inverse y by x. I want to check whether this function is the homogeneous or not. First I will go in the of that definition. Replace x by tx and y by ty. So here replace x by this is tx and y by ty. Therefore f of tx comma ty, which is equal to, so here tx to the power 1 by 3, ty to the power 1 by 4. This is 1 by 4 here, and tan inverse here, this is ty and this is tx. Now which is equal to, just replace, just x to the power 1 by 3, y to the power 1 by 3 and t to the power 1 by 3 into t to the power 1 by 4. So here t to the power 1 by 3, t to the power 1 by 4 into tan inverse, this is here t gets cancelled, this is y by x. Now this is equal to t to the power 1 by 3. So here 1 by 3 plus 1 by 4. Now here make denominator 12. So here 4 by 12 plus 3 by this is 12, which is equal to 7 by this is 12. Now here 1 by 4, yes, 7 by 12. So this is my t to the power 7 by 12 times here y to the power x to the power 1 by 3, y to the power 1 by 4 times tan inverse, this is y by x. Now just 1 by 3, 1 by 4, k to the power 1 by 3 plus 1 by 4. So here 4. Okay. So here this is equal to, t to the power 7 by 12 times f of x comma y. So here this is the homogeneous function of degree, we can say 7 by 12. So here this is again a homogeneous function. So here this is my homogeneous function. So here this is my homogeneous function of degree 7 by 12. Now here I want to check this example 8. Now here I will write my example 8. So here example 8 is defined as f of x comma y, which is equal to, so here x to the power 1 by 3 times y to the power 1 by 3 plus x to the power 2 by 3 and y to the power this is 1 by 3. So here this is my 1 by 3. If I get example, f of x comma y equal to x to the power 1 by 3, y to the power 1 by 3 plus x to the power 2 by 3 and y to the power 1 by 3. Now just replace x by tx and y by this is ty. So here f of tx comma ty, which is equal to, now tell me here tx. So this is tx to the power 1 by 3. Here ty to the power 1 by 3. This is tx to the power 2 by 3. This is ty to the power 1 by 3, which is equal to, here t to the power 1 by 3, t to the power 1 by 3, x to the power 1 by 3, y to the power 1 by 3 plus, here this is t to the power 2 by 3, x to the power 2 by 3, t to the power 1 by 3 and y to the power 1 by 3. Now which is equal to, here just observe one thing, this is t to the power 1 by 3 plus 1 by 3, this is 2 by 3 and x to the power 1 by 3 and y to the power 1 by 3 plus, now t to the power 1 by 3 and t to the power 2 by 3, t to the power 1 by 3, this becomes t to the power 3 by 3 and x to the power 2 by 3 and y to the power 1 by 3, which is equal to t to the power 2 by 3, x to the power 1 by 3, y to the power 1 by 3 plus t to the power, here 1 by 3 gets cancelled, 1, 3 by 3 gets cancelled, this is x to the power 2 by 3 and y to the power 1 by 3. So here we can't write, this is same as, here we can't write this function in terms of t to the power something times f of x comma y. So here this is not a homogeneous function, so here we can't write this same as n times f of x comma y, because power of t is different and power of t is different. So here we can't write this function in terms of this. So here this is my not a homogeneous function of degree. So here this is my non-homogeneous function. Now come to the example number 9. Now here example number 9 is defined as f of x comma y, which is equal to, so x to the power 3 plus y to the power 3 to the power 3 by 2. Here x to the power 3 plus y to the power 3 whole to the power 3 by 2. Now I want to check whether this function is homogeneous or not. Here replace x by tx and y by ty. So here f of x comma y, which is equal to, f of tx comma ty, f of tx comma ty, which is equal to, here tx whole cube plus ty whole cube to the power 3 by 2. So which is equal to, here t cube, this is x cube, plus t cube, this is y cube, this is 3 by 2. So which is equal to, here I will take t to the power 3 common. So here, and this is x cube plus y cube, and this is power 3 by 2. So which is equal to t to the power 3 into 3 by 2 into x cube plus y cube to the power 3 by 2, which is equal to t to the power 9 by 2. This is x cube plus y cube to the power 3 by 2. So this is equal to t to the power something. Here t to the power 9 by 2 times f of x comma y. So here this is the homogeneous function of degree 9 by 2. So here this is my homogeneous function of degree 9 by, this is 2. So here in this way you can check whether the given function is a homogeneous function of degree n or not. So here with this, now I want to discuss the Euler theorem. So here the statement of the Euler theorem says, so here if you have the function, so here Euler theorem says the statement of the Euler theorem says, now I want to prove the Euler theorems. So Euler theorem says, so just now we have discussed the homogeneous function of degree n. So now I want to discuss the Euler theorem. So the statement of the Euler theorem says, here statement of the Euler theorem says, if f of x comma y is a homogeneous function of degree n, then let's say here I will write z equal to f of x comma y. So here z equal to f of x comma y is a homogeneous function of degree n, then x times dou z by dou x plus y times dou z by dou y equal to n times, here I will write this is z. So here z equal to f of x comma y. Now so this is the statement of my Euler theorem. I want to prove this statement with the help of the definition of homogeneous function. Now the proof of the Euler theorem, here given function z equal to f of x comma y is a homogeneous function of degree n. So here given thing, let here given z equal to f of x comma y is a homogeneous function of degree n. This is given information. So here if z equal to f of x comma y is a homogeneous function of degree n, then z can be written as, so here I am writing, then z can be written as x to the power n times f of y by x. So here if function f of x comma y, that is z equal to f of x comma y, is a homogeneous function of degree n, then z can be written as z equal to x to the power n f of x by y. Let's say this is my equation 1. Now I want to show that x dou z by dou x plus y dou z by dou y equal to n times z. So here differentiate partially this equation with respect to x. So here differentiate partially with respect to x, equation 1. Equation 1, partially differentiate equation 1 with respect to x. So this is equal to dou z by dou x, which is equal to, so here first as it is, that is here here I will take, this is first product of two function. So here first as it is into derivative of second f dash of y by x into derivative of y by x is minus y by x square plus, this is plus f of y by x into derivative of x to the power n, that is n times x to the power n minus 1. Now which is equal to, here I will write the same thing, here minus y, here x to the power n minus 2 f dash of y by x plus n times x to the power n minus 1 into f of y by x. I will give this as equation number 2. Now partially differentiate this equation 1 again with respect to y. So this is z with respect to y. Differentiate here, differentiate equation 1 partially with respect to, let's say, y. So here this is dou z by dou y, which is equal to, now here while taking partial derivative of z with respect to x, at that time treat y as a constant. Now I want to take partial derivative of z with respect to y, here I will treat x as a constant. So here x to the power n is my constant and derivative is f dash of y by x into, this is 1 by, this is x. So which is equal to x to the power n minus 1 into f dash of y by x. This is my equation number 3. Now multiply equation 2 by x and 3 by y and add this equation. So here multiply left hand side and right hand side of equation 2 by x and equation 3 by y and add. So that is here x times, so here I am multiplying x into dou z by dou x plus, here I will add right hand side first, y times dou z by dou y equal to, here multiply x by equation 2 and y by equation 3, that is, and after that add equation 2 and 3 after multiplying x by x2 y, x by 2 and equation 3 by y. So add left hand side and right hand side. So here I want to multiply x here. So here this is my y, x into x to the power, this is n minus 2, this is f dash of y by x. Now here again plus, this is n times x to the power n minus 1, this is f of y by x. Now here plus, so here plus x to the power, here sorry I want to multiply second by y. So here y times x to the power n minus 1 into f dash of y by x. Now which is equal to, here x dou z by dou x plus y dou z by dou y equal to, here this is equal to minus y times x to the power 1 x to the power n minus 2, this is x to the power n minus 1, this is f dash of y by x plus n times x to the power 1 x to the power n minus 1, x to the power n into f of y by x. And now here this is plus y times x to the power n minus 1 into f dash of y by x. Now so here this is my positive quantity and this is my negative quantity. So here this cancel with this, which is equal to, here I will write here, which is equal to x times dou z by dou x plus y times dou z by dou y equal to n times, let's say I will write this as, here I will write this equal to x to the power n f of y by x, which is equal to n times, this is z, my z equal to from equation 2. So here z equal to x to the power n f of y by x from, this is from 1. Now this is the proof of my Euler theorem. The statement of the Euler theorem says, if the f of x comma y is a homogeneous function of degree n, then x dou z by dou x plus y dou z by dou y equal to n times z. This is the statement of Euler theorem. For all x comma y belongs to the domain of function. That is, for all x comma y belongs to the domain of my function f. Now, so sometimes in the exam they will ask verify the Euler theorem for the function so and so. So here, how to verify the Euler theorem for some function? So here I will write some example. So here, let's say for example 1. So here, verify Euler theorem. So here, Euler theorem for f of x comma y equal to x square plus xy plus y square. The statement of the Euler theorem says if the function is homogeneous function of degree n, then x dou f by dou x plus y dou f by dou y equal to n times that function f of x comma y. So here, of course, this is my homogeneous function of degree 2. Here, verify the Euler theorem for this function. Of course, this function is my homogeneous. So here, let's say this is my example 1. So here, how to write the answer? Since given function f of x comma y is a homogeneous function of degree 2, as f of x comma y equal to x square plus xy plus y square. So here this is the given function. Since given function f of x comma y is a homogeneous function of degree 2, therefore f of x comma y equal to x square plus xy plus y square. This is given function. And so here I want to show I want to prove this given function is the given function verify the condition of the Euler theorem. So here, if this is the given function, let's say z equal to f of x comma y equal to x square plus xy plus 1. This is the homogeneous function of degree 2 because degree of each term. So this is my first term, degree is 2, second term degree 2, and third term degree 2. So here, this is the homogeneous function of degree 2. Now here, find dou z by dou x. So we have to prove here. We have to show here dou x dou z by dou x plus y dou z by dou y equal to n times f of x comma y, where n is the degree of this function. Here in this case n equal to 2. So now here I will take left hand side. So here, for that purpose I want to find dou z by dou x and dou z by dou y. So here dou z by dou x equal to, so here partial derivative of this function with respect to x, treat y as a constant. Therefore 2x plus derivative of xy, that is with respect to y, and this is constant 0, and partial derivative of z with respect to y, which is equal to, so here x plus this is y. Now here, therefore according to this definition, x times dou z by dou x plus y times dou z by dou y equal to, now tell me x times, so here x dou z by dou x is, this is here 2x plus y times dou z by dou y. So this is x plus 2y, which is equal to, here this is 2x square plus xy plus y x plus 2y square. This is equal to 2x square plus 2xy plus 2y square. Take 2 common, x square plus xy plus y square, which is equal to 2 times f of x comma y. So this is hence the right hand side. Therefore the given function f of x comma y equal to x square plus xy plus y square verify. So here verify the condition of the Euler theorem. In the same way, I want to check whether my second function f of x comma y equal to x square plus y square satisfy the condition of the Euler theorem or not. So for that purpose, so my function should be homogeneous function of degree something. So here but here this function is not satisfy the condition of Euler theorem because this is my non-homogeneous function. So here we can't, so you can write if they said check whether the given function satisfy the Euler theorem or not. So here, but the given function is x square plus xy. This is non-homogeneous, so Euler theorem is not applicable for this function. So but here second function f of x comma y equal to x square plus y square is homogeneous function of degree 2. So you can apply the Euler theorem and we can apply the Euler theorem. After that we have to check whether the given condition, whether the given statement satisfied, whether the given statement of the Euler theorem satisfied by the function f of x comma y equal to x square plus y square or not. Now here I will write now here I want to check whether my given function f of x comma y here to verify the Euler theorem for this function. Let's say f of x comma y equal to x square plus y square. This is the, of course, this is the homogeneous function of degree 2. So here degree of first term is 2, degree of second term is 2. So that's why this is the homogeneous function of degree 2. So here this is homogeneous function of degree 2. Therefore now here first condition means the necessary condition for Euler theorem is the function should be homogeneous. So here given function f of x comma y equal to x square plus y square is the homogeneous function of degree 2. Now we have to show here, we have to show x times here dou f by dou x plus y times dou f by dou y equal to here n is 2 n times f of x comma y. So we have to show this. So this is the statement of my Euler theorem. So here for that purpose find dou f by dou x. So here dou f by dou x which is equal to partial derivative of my function with respect to x. So this is my 2 times x. Partial derivative of f with respect to y. This is my 2 times y. So here x times dou f by dou x plus y times dou f by dou y equal to so here x times dou f by dou x is, this is my 2x plus y times this is 2y which is equal to 2x square plus 2y square which is equal to 2 times x square plus y square which is equal to 2 times f of x comma y. Hence the result. Therefore the given function satisfy the condition of Euler theorem. Therefore for this function Euler theorem is verified. Now here check for example 4. Let's say I want to verify the Euler theorem for f of x comma y comma z equal to this. So here now example 4 says here function defined as f of x comma y comma z which is equal to xy plus yz plus this is xz. So of course this is the homogeneous function of degree 2. Why? This is my first term, this is my second term, this is my third term. Degree of first term 2, degree of second term 2 and degree of my third term is again 2. So here this is the homogeneous function of degree 2. If this is the homogeneous function of degree 2, so here now we have to verify the statement of the Euler theorem for this function, whether this function satisfy the condition of Euler theorem or not. So here this is my f of x comma y comma z. This is the function of 3 variable. So here for 3 variable the statement of the Euler theorem. So we have to show that. So we have to show that we have to show that here x times dou f by dou x plus y times dou f by dou y plus z times dou f by dou z equal to n times here this is f of x comma y comma z. So here in this case this is my homogeneous function of degree 2. So here in this case the value of n is 2. So here I want to show left hand side equal to right hand side. So here first I will find dou f by dou x. So here dou f by dou x equal to partial derivative of my function with respect to x. Treat y and z as a constant. So here this is y plus, so here x, so complete is constant, here this is 0, so here this is z. Now partial derivative of my function with respect to y. So here now this is x, so plus, so here this is z, so here no term y, complete term is 0. So here this is dou f by dou z, partial derivative of my function with respect to z. So here there is no z term, so this is complete term is constant 0. So here 1 z, so this is y plus this is x. Here just observe one thing, partial derivative of this function with respect to x. While taking the partial derivative with respect to x, treat y and z as a constant. So here y is constant, derivative of x with respect to x is 1, so this is y, and so y is constant, z is constant, derivative of constant is 0, 0, and z is constant, x is variable, derivative of this function with respect to x is x, with respect to x is 1, so z as it is. So this is y plus z, x plus z, and y plus x. Now according to this condition, x times dou f by dou x plus y times dou f by dou y plus z times dou f by dou z equal to now x times, so this is my x, dou f by dou x is, so this is y plus z plus y times, so this is y times dou f by dou y, this is x plus z plus, so plus z times, so this is my z times y plus here y plus x. So just multiply this bracket, so this is xy, this is xz, this is xy, this is yz, this is zy, this is xz. So here which is equal to, this is xy, this is xy, so here 2 times xy, this is yz, and this is yz, so here 2 times yz, this is 2 times xz, which is equal to 2 times xy plus yz plus x and z, which is equal to 2 times f of x comma y comma z. So this is the statement of my Euler theorem. Therefore the given function verified. So for this function Euler theorem is verified. Therefore here for f of x comma y comma z, Euler theorem is verified. Euler theorem is verified. So here this is the way. Now here in this way we can solve for any function. So here this is the complete concept of Euler theorems with homogeneous function. So here whenever in the exam they will ask, so here verify the Euler theorem. So at that time, so here this is the complete concept of Euler theorem and homogeneous function. So most of the time in exam they will ask, check whether the given function is homogeneous or not. So here if they ask, so here the definition of the homogeneous function, here if function f of x comma y is a homogeneous function, of degree n, then just replace x by tx and y by ty, then check f of tx comma ty equal to t to the power n times f of x comma y. If this condition is satisfied by your given function, then we can say your function is the homogeneous function of degree n, or in general term, so here if the function given function is the homogeneous function or not, so here check the degree of each term is same or not. So here this is my function is a homogeneous because degree of first term is 2, degree of second term is 2, and degree of third term is again 2. So here how to find? So let's say here again I will explain. F of x comma y equal to x square plus x y
plus this is y square. Here write this same as here y to the power 0 x square plus x y plus x to the power 0, this is y square. So here how to find the degree of, this is my first term, this is my second term, and this is my third term. So here how to find degree of first term? Degree of first term equal to power of x plus power of y. So here power of x in my first term is 2 and power of y in my first term is 0, which is equal to 2. So here degree of second term. So here degree of second term equal to power of here again power of x plus power of here y. So power of x is here 1 plus power of y is 1, which is equal to 2. And degree of third term, which is equal to power of again x plus power of again y. Here power of x is 0, power of y is 2, which is equal to 2. Therefore degree of first term is 2, degree of second term is 2, degree of third term is 2. That's why this is my homogeneous. Or else you can check with the help of this condition. So this is the way to check whether the given function is homogeneous or not. So after checking if your given function is homogeneous, then we can go for the statement of the Euler theorem. If the statement of the Euler theorem says if f of x comma y is a homogeneous function of degree n, then x times dou f by dou x plus y times dou f by dou y equal to n times this is f of x comma y. This is true for all x comma y belongs to the domain of my function f. So here this is the statement of my Euler theorem. So maybe sometimes in the exam they will ask verify the Euler theorem for so and so function. First we have to check whether the given function is homogeneous or not. So for example, if they ask third example f of x comma y equal to x square plus y, so this is non-homogeneous function. So you can say for this function Euler theorem is not applicable. If the given function is homogeneous of degree anything, at that time check this condition is satisfied or not. If this condition is satisfied, then at that time you can say the given function is verified the condition of the Euler theorem, that is x dou f by dou x plus y dou f by dou y equal to n times f of x comma y. In this way we can solve any problem about homogeneous function or Euler theorem in exam. Okay, thank you.